Good morning, Jeff. Good morning, Alana. Gonna wait a couple minutes until people join. Morning, Jamie. Recording. All right, a couple quick things. Let me just, while people are joining, let me share just a couple things in terms of your online resources page. So one big thing is our first celebration is going to be this coming Saturday. So today I'm going to talk about chapter 26, finish it on Thursday, do a little bit of a review. But celebration, just as an upcoming warning, it's going to be due by this coming Saturday. You can access it starting Friday about 8 a.m. I'll talk a little bit more about that on Thursday. But I wanted to throw out that I added the little section here for solutions to your online homework and quizzes. So people have been asking for that. So that is available. All right, let me stop that for a second. Before I just start lecture on chapter 26, just want to see if anybody has any general questions I can answer before we jump into it. Questions? If not, we're going to start chapter 26. All right, then. Let me just manage participants here. Open up chat just in case. Okay. Share this. So chapter 26 is all about properties of light. And according to Einstein, light is basically the coolest thing in the universe. And I would have to agree, light is pretty damn amazing. So what we're going to do in this chapter, why is that giving me this? Let's do draw. Let's use red. Morning, got a question there, Brian? No. All right. Mute people. Okay. So what I'm going to do today is I'm going to talk about electromagnetic waves, give you a little introduction, talk about electromagnetic spectrum, and that's probably, and then maybe I'll talk a little bit about transparent and opaque materials. But today I really want to just focus on introducing electromagnetic waves and the electromagnetic spectrum. We'll see how far we go. I'm still feeling a little bit under the weather. So again, it's kind of a bit weird, but can't really show you this. But what I was going to do is start with an introduction or show a little demo where I, if you remember, had a plastic rod and then I could rub it with wool to charge the rod and then attract a pith ball. So if you imagine this was just a charged rod that I charged just by rubbing it with wool. If it's stationary, remember, surrounding every stationary charged particle is an electric field. But also remember, if the particle is moving, not only does it have an electric field around it, but it also has a magnetic field. So if I had a charged rod and I started to oscillate it back and forth, what we're going to see is all light, remember, all waves are produced by something which is oscillating back and forth. And the frequency of the oscillating object is going to be the same as the frequency of the wave it produces. So for sound, whatever frequency your vocal cords are oscillating back and forth at, that's going to be the frequency of the sound wave. So I could produce a high sound wave if they oscillate back and forth very rapidly, or a low sound wave if they oscillate back and forth not as rapidly. Well, light is also produced by an oscillating object. And in general, it's usually electrons which are oscillating up and down, back and forth. And an oscillating charge will create an electric field, which is oscillating back and forth. And one of the things that we're going to talk a little bit about is a changing electric field will create a changing magnetic field, and a changing magnetic field will create a changing electric field. So I'm only going to ask you to sort of think about this conceptually, because trying to think about electric and magnetic fields is a very sort of challenging concept. But let me see if I can show you just a quick little, well, let's just go to PowerPoint slides real quick. kind of hard to visualize, but when I have an electric field, which is changing, one of the things that Einstein discovered is that a changing electric field will create a changing magnetic field, and a changing magnetic field will create a changing electric field. So let me try and do a new share here. Let's go to, oh, that's not going. Stop that for a second. Animations. I'm going to show you this. Oh, I know where it is. 1 second. New share. Okay, so you can't really see on this, but there is right here, this might be an electron, which is oscillating up and down. That oscillating electron is going to create an electric field, which is changing with time. It's not constant. And that changing electric field, in turn, is going to create a changing magnetic field in blue. You don't need to worry about all of that. But our brains then get this light, and we'll talk a little bit. We have these things in our eyes called rods and cones. And whenever they have light hit it, basically they send a signal to our brain, and then our brain interprets that as light. And we'll talk more about color and stuff like that in chapter 27. But anytime I have a charge which is moving up and down. So here's a good example. Can everybody see this? Can't tell if it's being shared. Let me just stop this.
Yes, I can see it.
Okay, well, now I will share it again. So this is basically a model of...
Now we can't see it.
Now you can't?
I'm just kidding.
Oh, it's too early for that. All radio stations are basically one giant antenna, which has an well, not an electron, it has many, many electrons in it. These electrons will then oscillate up and down, and an electron which is oscillating up and down is going to create basically light. In this case, it's a radio wave, but we'll see the only difference between radio waves and ultraviolet and microwaves is just different frequencies and different wavelengths. So what happens is this antenna, which has these electrons oscillating up and down, creates this creates this radio wave, which then is traveling outwards. And then what happens is this is a receiving antenna. And in fact, this just could be the antenna of your car. It has a bunch of electrons in it that are free to move. And when the radio wave hits the electrons, it causes them to oscillate up and down in your antenna. And that's basically how you receive a radio wave. So let me stop that and then just go back to So you don't really need to worry too much about electric and magnetic fields, what actually they're doing. Just think about all light is created by some oscillating charge that moves up and down, back and forth. Anytime I have a charge which is oscillating, around it is an electric field and a magnetic field which oscillates, and that's really what light is. Okay, so a little summary. Light, keep in mind, is a transverse wave. And remember, a transverse wave is one in which the disturbance is perpendicular to the direction of travel of the wave. And it's always being created by some kind of electric charge which are accelerating, or they're oscillating up and down. Remember, every charge that is moving has both an electric field around it and a magnetic field. If a charge is at rest, it only has an electric field around it, but if it's moving, it has both. Well, if the charge is oscillating, which basically means vibrating, then the electric and magnetic fields will also oscillate. And one of the things that Einstein discovered was that anytime I have an electric field which is changing, that's going to create a magnetic field. And anytime I have a magnetic field that's changing, that's going to create an electric field. And so it's really cool. Light is produced by something out in space. You know, you have the sun or something like that. But then as the light is traveling through space or through anything, the changing electric field is going to create a changing magnetic field. The changing magnetic field is going to create a changing electric field. And in essence, these things just continue to recreate each other as this wave is traveling through space. So at the most general level, an electromagnetic wave is just oscillating electric and magnetic fields. And again, we interpret light in a specific way that I'll talk about in chapter 27, how we see colors and things like that. But one important thing, the first super duper important thing from this chapter is all electromagnetic waves in space, in a vacuum, where there's no air or anything like that, they all travel at the same speed. That speed, the speed of light.
Can you repeat that? What you just said?
All electromagnetic waves in a vacuum travel at exactly the same speed. We call that the speed of light. We give it the symbol c. And just in terms of units that we're used to, it's about 186,000 miles per second, not miles per hour. So in 1 second, light will travel about 186,000 miles. Unfortunately, we're not going to have time to get to relativity, but light is the fastest thing in the universe. According to Einstein, and it's been tested countless times, nothing can travel faster than the speed of light. Nothing. It is the ultimate speed limit in the universe. And as things start to approach the speed of light, very interesting things happen. Time slows down, lengths contract. Well, I won't go into all that, but the speed of light is the fastest thing in the universe. So if you remember, the one big equation for all waves is that wavelength times frequency equals wave speed, right? This is true for all waves. But if we're talking about light, light in a vacuum travels at c. So basically what we have is the wavelength of light times the frequency of light is going to be equal to the wave speed, which for light, we just indicate with c. So an interesting thing is, let me just touch on this real quick. Well, let me actually start here. Little question in the voice of Outer Limits. Imagine, if you can, the worldview of little creatures who could only see a very tiny portion of the visible spectrum. Creatures who are colorblind to all other parts. Their world would be very limited. So let's say that a certain creature could only see a very narrow range of red. Anything that's not red, this creature can't see. Well, you can imagine you'd have a pretty limited worldview. Well, guess what? We are like those little creatures in that the spectrum of colors we can see are only a very tiny portion of the entire electromagnetic spectrum. Meaning, if I were to look at all the different kinds of light there are, and we'll talk a little bit about this later, but we go all the way from radio waves, which have the longest wavelength and the shortest frequency, all the way up to gamma rays. These have the smallest wavelength and the highest frequency. If you look, visible light is just a very, 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 very small portion of all the light that's out there. So whenever we talk about the electromagnetic spectrum, we're talking about basically all the frequencies of light that there are. So we have radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. And if I were to look at the entire spectrum, you don't need to know this number, but visible light makes up less than 1/1,000,000th of 1% of the entire electromagnetic spectrum. So basically, we are blind to all forms of light except this very, very narrow region of the electromagnetic spectrum that we are sensitive to. Now, some people can see higher frequencies than others. Some animals can see into the ultraviolet portion of the spectrum, but we as humans can only see a very, very small portion of the entire electromagnetic spectrum. And it's just light that, where's my thing? Did I turn this off? Okay, so in terms of the spectrum, we're going to go through this, but you've probably heard of Roy G. Biv before. It's just a way of indicating the colors. So we've got red, orange, yellow, green, blue, indigo, and violet. So red, we'll see, you don't need to know these exact values, but red is the lowest frequency light that we can see. Violet is the highest frequency light that we can see. And this is going to be important once we get to chapter 27 when talking about how we see different colors and things like that. The spectrum goes from Roy G. Biv in terms of lower wavelengths up to higher wavelengths. I'm sorry, lower frequencies up to higher frequencies. So let me just do that over here. Red, orange, and yellow. These are considered sort of the low frequency light. Green is sort of considered mid frequency. And then blue, indigo, and violet are all considered sort of high frequencies. Again, this will come important later. But I just wanted to emphasize that when we talk about the electromagnetic spectrum, it's all the forms of light that exist. Lowest energy, lowest frequencies are microwaves and radio waves. Highest energy, highest frequencies are X-rays and gamma rays. Okay, let me stop that for 1 second. Oops, I don't want to do that. I just open it up for a second to see if there's any questions on anything I've talked about so far with the electromagnetic spectrum. Gone once, gone twice.
That was easy.
Woohoo! All right, let's go back. Share screen, let's do this again. All right, so as I was saying, visible light is just an electromagnetic wave, and it's no real difference between visible light and ultraviolet and microwaves except for wavelength and frequency. They're all identical. It's just like sound waves. A high frequency sound wave is no different than a low frequency sound wave. The whole spectrum consists of all different forms of light, and we can only see this very tiny portion that goes from about 4 times 10 to the 14 hertz to 7 times 10 to the 14 hertz. Again, you don't need to worry about that number, but 10 to the 14, as you probably know, means there's like 7 times 10 to the 14. Let's just write that out. Is 7, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. This is the frequency of violet light. If you remember, hertz means per second. So if something has a frequency of 60 hertz, that means it's oscillating back and forth 60 times a second. Well, if violet light has a frequency of 7 times 10 to the 14 hertz, that means whatever's producing that light, which is generally an electron, is oscillating back and forth 7 times 10 to the 14 times a second. So what is that? A billion is 10 to the 9. A trillion is 10 to the 12. So this is 700 trillion times a second, which is how often something would be oscillating back and forth to produce visible light. Badass, right? Okay. So in terms of the electromagnetic spectrum, as I was saying, it consists of electromagnetic waves of all frequencies. Radio waves, these are the lowest frequency, highest wavelength. And gamma rays, these are the highest frequency, smallest wavelengths. And as I was saying, visible light is only a very, very, very tiny portion. You don't need to know the number, but less than a millionth of 1%. So a couple things I wanted to mention about this speed of light. I'll just do that here. So this speed, remember, of light is 186,000 miles per second. So here's a really cool concept to think about. Light doesn't travel infinitely fast. So if something's producing light, it's going to take a little time for that light to get from the object to us. Does anybody know how long it takes light from the sun to reach us?
7 minutes.
How much would you say?
Is it 7?
It's about 8 minutes.
Oh.
So what we say is the sun is 8 light minutes away. which basically means it takes light from the sun 8 minutes to get to us. If you've ever heard of a light year before, a light year is actually a unit of distance, right? In space, distances are so vast, it doesn't make sense to measure things in miles. We measure it in light years, and a light year is how far light travels in a year. It's about 6 trillion miles. It's an insane number. The closest star to us is about 4.3 light years away, which means this. The light from that star took 4.3 years to get to us. Actually, let me just stop this share for a second. I want to show you my big face because this is a super cool concept. So light from the sun takes 8 minutes to get from the sun through space to the Earth. Light from our closest star that's not the sun is this, Alpha Centauri. It's about 4.3 light years away, which means it takes light from Alpha Centauri 4.3 years to travel through space to get to us. Here's why that's cool. When you look up at the star, let's say we're just looking up at Alpha Centauri, what you're seeing is the star as it was 4.3 years ago when the light first left the star and is finally just now reaching the Earth. So thinking along those lines, here's a fun little question for you. Clicker questions. So 26.1, it says, when you look at the sun, we are seeing it as it was 8 minutes ago. So we can only see the sun in the past. When you look at the back of your own hand, do you see it now or in the past? So I'm holding my hand up and I'm looking at the back of my hand.
In the
Am I
past.
seeing my hand in now or in the past? And believe it or not, the correct answer is in the past. Why? It does take light a tiny, tiny, tiny bit of time to travel from my hand to my eye. It's less than a billionth of a second, but technically, when I'm looking at the back of my hand, I'm now seeing it as it was a billionth of a second ago. So here's one thing that's really cool about this. You go camping somewhere where you can see hundreds of thousands of stars. There's a good chance that some of those stars don't even exist anymore. They went supernova, they exploded. Let's say a star was 1,000 light years away. If it suddenly just disappeared off the face of the universe, we wouldn't know about it for 1,000 years because every time we see light from that star, it's the light that left 1,000 years ago and is just reaching us now. Pretty cool concept. So what this means is that you can't see, let me stop this for a second. Everything you see every day of your life has already taken place. Now, if we're talking about just looking at something close, like my hand, I'm seeing my hand as it was, a 10 billionth of a second ago. But if we're looking at distant galaxies, like Hubble telescope has seen galaxies and quasars that are like 12 billion light years away, which means we are literally looking into the past 12 billion years because the light we see from that star left 12 billion years ago and is just now getting to us. So if our sun just disappeared for some reason, I could snap my fingers. I got the infinity stones and I could snap my fingers and get rid of the sun. We wouldn't know about it for 8 minutes because all of the light that we're getting from the sun is 8 minutes old. So let me pause that for 1 second. I'm not sharing. So I want to open it up for any questions about that because that's a really kind of cool concept. So light doesn't travel infinitely fast. It does take time to go from one object to another. The farther away those objects are, the longer it takes the light to travel. And if we're talking about stars out in space, the closest star, it took light 4.3 years to get from that star to our sun. Some of the farther away stars that can take tens of thousands of years, millions of years, even billions of years, which means when we look up into the night sky, we are looking into the past and seeing light that left many, many, many years ago. Do, 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 do. So let me pause. Questions I can answer on that very cool concept? Gone once. Gone twice. That was easy.
That was easy.
All right, let's go back. Oh, we did cover that. So what do we got? Oh, so I can talk about transparent materials and opaque and that. Okay, well, sweet. We're doing pretty well. All right, so what I want to talk about now is how does light get through a transparent material like glass? And this is an image I got from your book, which I really like. And it's basically showing that how light gets from one material through another. So one, let's just be clear, if I'm talking about a transparent material, this is just a material that you can see through, right? Something like glass or water or things like that. How does light get through water? How does light get through glass? Well, it's this process of constantly being absorbed and then re-emitted by electrons in the material. So what happens is you've got light coming in, and let's just say this is a pane of glass right here, and I've got this bit of light coming in, and that light's going to pass through the glass and get to the other side. Well, what is that process? Well, what ends up happening, and this is kind of cool, is the light comes in, and when it hits sort of the first atom in the glass, what ends up happening is that atom, an electron in that atom will absorb the light, and that light completely disappears from the universe. Very cool. So the light's coming in, hits a atom, the electrons in the atom absorb the light, and the electron starts to oscillate up and down at the same frequency the light had. Well, that oscillating electron will then produce its own light and pass it along. And what happens is, so this light comes in and gets absorbed by an atom here, causes it to oscillate up and down, and that atom then creates its own light. Your book is kind of showing it like the atom gulps up the light and then burps it up. And then the next atom gulps up the light and then burps it up. And that process of gulping and burping continues until the light gets to the other side of the glass. Now, obviously, that's not like the atom is eating the light and then burping it up, but it's kind of a fun little image to think about. What's really happening is, I guess I jumped ahead a little, I got a little bit ahead of myself. Let me just go back and talk really about transparent materials and opaque. So one, I think I've mentioned this a couple times. If light hits a surface, or if a wave hits a surface, there's three possibilities for what could happen. That could either be reflected, it could be absorbed, or it could be transmitted, or generally some combination of all three. So for example, glass. I have light that hits glass, that light can get reflected. How do I know that? Well, I can see my reflection in a plane of glass. That light can get absorbed. How do I know if light gets absorbed? Well, light has energy, and if an object absorbs light, it absorbs the energy that that light had and it'll heat up. Or it can pass through. How do I know for glass? Well, I can see on the other side of glass. Water's another case of something that can reflect light, it can absorb light, and it can let light go through it, which we just call being transmitted through. So a transparent material is one that allows light to pass through it. And the big thing, well, you're not really doing any essay questions for the celebration, but if you were, I would have asked you to explain for me how light passes through a transparent material. And the basic process is, what is happening when I do that? It is continually being absorbed and re-emitted by electrons that are being forced into vibration. So all light, in essence, well, I'm oversimplifying. Most light is created by electrons which are oscillating up and down. That oscillating up and down electron will create light at the same frequency it's oscillating at. Well, it's also possible for an electron to absorb light. And kind of cool, when an electron absorbs light, that light literally just disappears. It's gone from the universe. It doesn't exist anymore. But the energy that that light had, in essence, is getting transferred to the electron, which is going to cause the electron to oscillate up and down at the same frequency the light had. That oscillating electron will then emit light. And that light, oh, actually, I have a question for you then, even before I go through that. So, light going through a glass, and I'll go through the whole procedure in a second, is the light is coming in, it gets absorbed by, let's say, an atom here, one of the electrons absorbs it, and then it's going to re-emit that light. The question is, compared to the absorbed light, the frequency of the emitted light is considerably less, slightly less, the same, slightly more, or considerably more. So this light that comes in, you know, it's going to have a certain wavelength and a certain frequency. That's going to depend upon what color the light is, if it's visible, ultraviolet, and so on. That will then get absorbed by an atom, technically an electron in the atom, which will then re-emit the light. How do you think the re-emitted light compares to the absorbed light in terms of the frequency? And a hint to think about is, let's say I saw somebody on the other side of a clear plane of glass. Would the color of their shirt or pants or things like that change if it's just a clear piece of glass? And the answer is no. The fact that I see an object the same in front of a piece of glass as I do on the other side means the light that made it through that glass must have the same frequency of the light that got absorbed at the beginning. Otherwise, well, I guess I didn't tell you this. Well, I sort of did. The color that we see is really just different wavelengths and different frequencies. So what's the difference between red light and yellow light and green light? Red has a different wavelength and a different frequency than blue. Blue has a different wavelength and a different frequency than green. But there's no real difference between an electromagnetic wave that's visible light, an electromagnetic wave that's ultraviolet. The only difference is the wavelength and the frequency. Okay, so going back, here's a little piece of light.
Joe, so the answer to that one was the same.
So, oh yeah, I got ahead of myself. So the answer to this was, it is the same. So, you know, if this is some frequency, let's just say of red light, once this light eventually makes it all the way through the glass, it's going to have the exact same frequency red light it did before. So that's why things don't look a different color on one side of the glass as it does on the other. Now, let me just say that there are colored glass that will absorb or allow certain colors to go through it. But just in general, if we're talking about a plain sheet of glass that's not color polarized or anything like that, the frequency that makes it through the glass will be the same as the frequency that sort of hit the glass. Okay, so here's what's happening is, here's a little piece of light. And here's one atom of glass, one atom in the glass. So there's an electron in this atom. So again, also just to be specific is, I've got this light coming in, and here's just this pane of glass. And I want to know, how does this light eventually get to the other side of the glass? And it doesn't just pass straight through it. It's continually getting absorbed and then re-emitted and then absorbed and then re-emitted and then absorbed and then re-emitted many, 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 many times. So this right here below might just represent 3 of the many atoms that are in the glass. So this light comes to the very first atom, and it will absorb that light and then vibrate at the same frequency the light had. Now, here's the cool thing is, when the electron absorbs the light, ooh, oh, I thought I froze. It's literally no longer existing. But the energy that that light had got transferred to the electron, causes the electron to oscillate up and down at the same frequency the light had. Well, this oscillating electron will then create its own light. And that light will have the same frequency, the same wavelength as the absorbed light. So it is identical in every way, but it is a new piece of light. So if I could somehow put a little tag on this light that's coming into the glass, a little name tag, when it gets absorbed by the electron, it's done. It no longer exists. But that oscillating electron will then emit another piece of light, which is identical in every single way to the light that was absorbed. But technically, it's a new piece of light. It didn't exist before. The oscillating electron created it. So this light comes in, gets absorbed, causes these electrons in here to oscillate up and down, that they then produce their own light. That light has the same frequency and same wavelengths. And then this atom will now absorb this new piece of light. And it's going to cause this atom's electrons to start oscillating up and down, which will then emit another piece of light, which is also identical. And then that'll cause this atom to start to oscillate, or electrons in this atom to oscillate up and down, which will then create a new piece of light. And this process of constantly getting absorbed and re-emitted, and absorbed and re-emitted, and absorbed and re-emitted continues the entire time until it eventually gets to the other side of the light, or the other side of the glass. So your book kind of has just this fun picture of saying that these atoms sort of gulp up the light and then burp it up and then gulp it up and then burp it and so on. But what's really happening is this atom, electrons in the atom will absorb that incoming light. Light is gone. The electrons will then oscillate at the same frequency the light had, emit new light. That new piece of light did not exist before, but it has the exact same frequency, the exact same wavelength as the original piece of light. So, kind of a cool concept. The light that leaves the glass, same frequency, however, it is new light. It's not the same light that entered the glass. So this leaving little bit of light is identical in every single way to this incoming piece of light, but technically it's a new thing of light. Meaning if I could somehow tag that original piece, you know, give it a little name tag or something, I would see that this light that leaves the glass is identical, but it's not the same. Okay, there was a clicker question, no. Oh, here's a question I wanted to ask you just about that. So pretend a person can walk only at a certain pace, no faster, no slower. If you time her uninterrupted walk across a room of known length, you can calculate her walking speed. If, however, she momentarily stops along the way to greet others in the room, the extra time spent in her brief interactions gives an average speed across, no? How is this like, oh, I guess I didn't cover exactly everything I needed to cover. So one last thing I wanted to say is, speed of light in a vacuum is constant. All light in a vacuum travels at exactly the same speed, 186,000 miles per second. So in between these atoms, so you've got these atoms that are absorbing light and re-emitting it. What's in between atoms? And the answer is nothing, right? Vacuum is basically the absence of anything. And if I look, I've got a bunch of atoms inside the glass, but what's in between the atoms? Nothing. So when light is traveling between these atoms before it gets absorbed by one atom and then re-emitted, it's traveling at the speed of light. But what happens is this process of gulping and then burping, or in reality, this process of getting absorbed and then re-emitted, is not an instantaneous process, which means that there's a small time delay between when light enters the glass and when it leaves. Even though light always travels at the same speed in a vacuum, if it gets absorbed and then re-emitted, in a sense, that's going to slow down how long it takes light to get from one end to the other, simply because it's getting absorbed and re-emitted, and that process takes a small fraction of a second. I don't know the exact number, it's like a millionth of a second or a billionth of a second, but if getting through the plane of glass, it has to get absorbed and re-emitted 10,000 times, 10 million times, that's going to cause the light to take longer to travel through glass than it would through a vacuum. So thinking about that, so well, one, Why would you expect the speed of light to be slightly less in the atmosphere than in a vacuum? Whoa, what happened there? Bump, PowerPoint. What happened? Well, the average speed of light will be less where it interacts with absorbing and re-emitting particles of matter, such as the atmosphere. The more it has to interact, the longer it's going to take to travel through a material. So even light traveling through our atmosphere, how does it get through our atmosphere? Well, by getting absorbed and re-emitted by whatever's in our atmosphere, mostly nitrogen and oxygen. So this is how light gets through a transparent material, is by getting absorbed, causing electrons in that atom to oscillate up and down at exactly the same frequency, which then emits light, which is identical to the original light, which then gets absorbed, re-emitted, and so on. So then thinking along those lines, and I think we'll end it here after I get this question. Pretend a person can walk only at a certain pace, no faster, no slower. If you time her uninterrupted walk across a room of known length, you can calculate her walking speed. If, however, she stops momentarily along the way to greet others in the room, the extra time spent in her brief interactions gives an average speed across the room that is less than her walking speed. How is this like light passing through glass? In what way is it not? So a person's walking through a room, and let's say every time they stop and they see somebody, they have a brief little interaction. Hey, how's it going? Blah, 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 blah. And they continue walking across the room, and then they stop and have another interaction, and then they continue walking across the room and so on. How is that like light passing through glass? And in what way is it not? And the answer is the following. So this is like light passing through glass because there is a slight delay between when light is absorbed and when it's re-emitted. Between atoms and molecules, light is always traveling at this constant speed of light. So that's sort of similar to the analogy we just gave of somebody who can walk across a room at only a certain speed every time. But then whenever they interact with somebody, they have this brief interaction, and then they walk across a little bit more, brief interaction, walk more, and so on. The way it's not like light is the light that entered the glass is not the same as the light that emerges from the glass. Every time it's basically new light. So in this analogy, how would this work? Well, if every time this person had an interaction with somebody else, I guess that person absorbed the other person and then somehow emitted an identical person who then walked across the room, had an interaction, somehow got absorbed in that interaction, and then re-emitted as an identical person. Okay, that's much of chapter 26. So on Thursday, I'm going to finish chapter 26 and then talk a little bit about the celebration. I've started making it up. My thoughts are it's going to be 50 multiple choice questions. You'll have 90 minutes to complete it, which will be more than enough time. You can access it starting Friday at about 8 a.m. It has to be done no later than Saturday by midnight. So I'm giving people sort of a 48-hour window, not quite 48 hours, but almost 2 days to do it. You'll have 90 minutes to complete the celebration once you start it. And it'll sort of be like the quizzes. It'll be generally straightforward. I'm hoping people are doing, well, actually I calculated your grades. Once I get the celebration number 2, I will give you your grades, but people are doing fairly well. So nobody should really be stressing too much about their grades. I will have grades emailed out next week once I have the second celebration graded. So that is sort of the end. So let's end the Physics 10 lecture portion of Zoom. No, I always forget. We're ending it. No, yeah. Ending the lecture portion, bringing in office hours. If anybody has any questions about anything I've covered today in chapters 26 or anything in Physics 10, I'll hang around until 10:45. If not, then thank you for joining me live, and I hope to see most of you again on Thursday. Thank you, everybody.
On last week's homework,
Yes.
On the ones that you don't have to correct, I put like 4 nodes instead of just 4 and got it incorrect. So I was wondering, are you just gonna go through and like manually fix those
Oh,
homework?
for the homeworks?
Yeah.
Oh yeah, don't go by the grades on mastering physics. So in essence, to get mastering physics to give a grade, I have to go through every single question and either mark it as 0, 50%, 100%. So what I did is I just downloaded all of your homework and then just quickly went through it. And as long as you answered everything, I gave people full credit.
Okay, cool. Because yeah, one of them, instead of putting 4, I put 4 nodes and I got wrong.
Yeah, so yeah, that's, I mean, I think if you look, all the homework shows 0% unless I specifically go in and grade it on mastering physics, and that's a pain in the butt. So I just download all of your homework, and then I quickly go through it, and pretty much everybody is getting hundreds on all the homework unless they didn't do it at all or just answered very, yeah. So yeah, you're fine.
Okay, thank you. That's
You're
it.
welcome.
I have a question.
Okay, what's up, Laura?
Would you compare the way that you just described the light going through and repeating itself through the wind, like through a transparent object? Would that be similar to resonance and sound?
What we're going to talk about is, yes. So on Thursday, I'll talk about opaque materials. So not all materials allow light to pass through it. Some materials are what's called opaque, which means they absorb the light without re-emitting it. And whether or not an object absorbs light depends upon the resonant frequency of that object compared to the frequency of light. What ends up happening, just as a little preview, is, remember, resonance is when you're exerting a force on something at the exact same frequency it wants to oscillate at. Like pushing a child on a swing and timing your pushes, so you're always pushing at just the right time. When that happens, you get a big increase in amplitude. Well, what happens is, if light comes in and gets absorbed by an object where the frequency that that object wants to oscillate at, which we call its resonant frequency, exactly matches the frequency of the light, rather than just oscillating a little bit and then passing the light on, doing work outside, it oscillates rapidly and starts to cause the electrons to move up and down a lot. And those electrons run into those electrons run into other electrons, and they lose their energy as heat rather than passing it along. Let me see. Hold on one second. Let's see if I can close my window. Ugh, sorry about that. The joys of working at home. So we'll talk about that more, Laura, but yeah, it does have to do with resonance. And if light matches the resonant frequency of, let's say, glass, it's not going to get passed along. It's going to get absorbed. And once we get the color, like the reason this shirt is blue is because I have white light shining on it. White light consists of light of all frequencies. And this shirt is absorbing, in essence, all frequencies of light except blue. Blue is what's getting reflected back to you, and that's the color that we see. So if you see something as red, that's because that object is absorbing all colors of light except red. Red is what's getting reflected back to you, and that's the color that you see for an opaque object, is the color of light it reflects back to you.
Awesome. Thanks for the discussion this morning.
You're welcome. Have a wonderful day.
Thank you.
Pedro, Jamie, any questions from you?
No, I'm good. I just wanted to hear that response. Thank
Okay.
you. See you
You're
Thursday.
welcome. See you Thursday. How about you, Pedro? You got a question for me? There's no questions. I'm just going to pause the video and mute it for a second. If you do have any questions, throw in a comment or ask it and I will hear it. I'm going to pause the recording for a second.